So in this lesson, we're going to look at the uses and dangers of alpha, beta and gamma. So if you've got the booklet, please add your date in up here. Let me just give you a little idea where we are. We're coming to the end of this topic. So we're looking at the uses of radioactive isotopes. So we've covered really the fundamental nature of what is alpha, beta and gamma, nuclear equations, half-life. So in this little lesson, we're just going to look at some of the issues behind being exposed to nuclear radiation and ionizing radiation, and then some of the uses in commerce and industry and in medicine. So if you haven't done this already, please go and look at, you've done this task in your booklet, so please go and have a look back at it and see if you put this there. So pause this now and I'll just recap some of the features of penetrating power of alpha, beta and gamma. Okay, so fundamentally, alpha radiation. Well, alpha radiation, as much as it's very good at ionizing, it's not particularly good at penetrating. So alpha cannot get through paper, aluminium foil, thin lead, thick lead, or even through the hand. So you're safe from alpha if it's on the outside of your body. The medium one for penetration power is, I suppose, beta. Fundamentally, you can get through paper. Aluminium foil, we can get through to a certain extent, depends how thick the foil is and exactly how strong the beta is, how much energy it has. But normally it's blocked by lead. I put a half here for the hand because it can sort of penetrate through the skin. But you know, it wouldn't take a lot of flesh for it to be blocked. And then we get to the most penetrating one, which is gamma. And you should have this idea that really gamma can get through pretty much everything. If you want to stop gamma, you're really going to need something like a really big, thick slab of concrete, a really thick or thick slab of lead to be safe behind it. Remember, gamma can travel kilometers through air. So let's with that in mind, let's just start looking at perhaps some of the dangers. Why ionizing radiation, that's alpha, beta and gamma for us, is dangerous. Well, fundamentally, alpha radiation, alpha, beta and gamma are all considered ionizing radiation. So I'm not going to ask you to pause it, but do you remember what ionizing means? Covered it a few times already, but I keep on coming back to it because it's really important. Alpha, ionizing. It means it can ionize atoms. And I think one of the key words here is the atoms bit, because only atoms can be ionized. You can't ionize cells. You can't ionize pieces of equipment. So when you talk about ionize, we talk about ionizing atoms. And what do I mean by that? Literally, I mean adding or removing electrons from the shells. So if you get that down in here. Now, if I was in the lesson now, I'd probably start talking about asking if anyone recognised this person. This is actually the same person. He was called Alexander Litvinenko, and he was actually poisoned by, well, the most wise people, I would say, or most commonly held view, that he was poisoned by Russian intelligence because he'd actually left Russia to come to the UK, and he used to work for the Secret Service for Russia. And what was generally recognised as happened is that they put some radioactive sources into his tea. So why would that be a bad thing for anyone to have? Well, let's just zoom up on this little chart here, and what we can see here is really just a breakdown of a little chart. You might be familiar with some of the parts of this. We're mainly made out of cells. That's the fundamental building block of living organisms. Inside the cell, we have the nucleus, not the same as the nucleus of the atom, but the nucleus of the cell. Inside the nucleus, we will have chromosomes, and chromosomes are made up of long strings of DNA. And on the DNA here, we can see base pairs. So fundamentally, what happened with Alexander Litvinenko was he was poisoned with a radioactive source. And the fundamental danger that ionizing radiation does is that it can ionize atoms in our genetic material. i.e. it can ionize atoms in the nucleus, it can ionize atoms in the chromosomes, it can ionize atoms in the DNA, it can ionize atoms in the base pairs, and if you ionize atoms in the base pairs, then you can actually cause some damage to the cell. And if that's extreme damage, then that could mean to cell death. Lower levels of damage might cause just unwanted mutations, which can lead to things like cancer. So fundamentally, what I'd like you to write in here, if you haven't got it already, is that the key idea is that atoms in the nucleus, DNA, chromosomes, or genetic material get ionized. So it's the atoms in here that get ionized. And what's the problem with this? It can lead to mutations in the cell, can cause an increased risk of cancer. Higher levels can lead to cell death. Okay. So that is fundamentally why we don't want to be exposed, and it's really important you get those two ideas there about there's two separate points to be made there. It's really like it's atoms and the genetic material, and then it's what are the dangers. Well, low level can cause mutations, and higher levels can cause cell death. Let's move on now to some uses of how ionizing radiation can be used. Let's look at this situation here. Here we have a pumping station. This pumping station is actually providing, it could be fuel, it could be gas, it could be water, and it's being pushed down to the pumping station along down here. Now, suppose at some stage we realise there is a leak somewhere. Well, this could be, we might have somewhere down here, a few kilometres down the line, we realise that we're not getting what we're pumping into this pipe. So how do we go about investigating where it is? Well, the old-fashioned way would be to just get in and start digging and digging and digging and digging and opening up this pipe so we could see it. And eventually we might find out where the leak was. And that would be, I suppose, a traditional old-fashioned way of doing it. A more modern way is to make use of radioactive isotopes. So if I inject some radioactive isotope into the fuel at the start or the water, now that doesn't necessarily mean it has to be super dangerous. It could be quite low levels of radioactive sources, and they could have a short half-life. And as I put them in, they will travel along the pipe. Now, where is the leak? Well, once I know I've got my radioactive sources flowing along the pipe, then what I can do is I can bring in my engineer with a Geiger Muller tube, and I can place that engineer, can go to various, I've got numerous copies of the engineer here so I can show them up and down, and they can go to various positions along the pipe, see where they're going to see what happens. Well, what's going to happen here? Round about here, if we use the right radioactive source, we're not going to get any reaction. And as we keep on going, no reaction. But as we start to find where the leak is, we might start to get some indicators on the Geiger Muller tube, because the Geiger Muller tube can detect the radioactive source where it leaks out of the pipe. So when you see in this position here, we can detect some of the radioactivity because it's leaked out of the pipe and then it's coming up close to the surface. So what type of radioactive source would we want to use for this? Well, the main one that we would use for this is beta. And the reason we'd want to use beta for this, I'll try and write that in there. I'm using a mouse for writing, which is not that great. It's because beta, if you remember, is moderately penetrating. And why do we want something that's only moderately penetrating? Well, fundamentally, if we go for alpha, then alpha, we put alpha in here. Well, the alpha's not going to get to the detectors anyway, because alpha's not very good at penetrating. Alpha can only even travel a few centimeters. So if you had a leak under the ground, even if some of the liquid was coming out in underneath the surface of the ground, you are not going to pick that up unless you actually, the leak literally came right up to the surface and you virtually put the detector right on top of it. So alpha would not be very good. The other one that wouldn't work for us is gamma, because gamma is so good at penetrating. If we had some radioactive sources in here and they were gamma, well, the gamma would just be able to emit even while it was in the pipe and under the ground. It wouldn't need to actually come out. So you'd actually just find the detector going off in all these situations if we were using gamma, anywhere when we're above the pipe, because gamma is such a good penetrator. So on this one, we only really want to use beta, because that's the one where we'll get an increase in the count rate, like this engineer has got here, when they're coming over here. So this is where we need to dig. So that's one use of beta radiation. Let's go to another one. Now this is a use of alpha. Now alpha is often used in these things. This is a smoke alarm. So let me just explain the fundamentals of what a smoke alarm is. If you open up a smoke alarm, you would find inside some sort of chamber with two plates. Now this lower plate here has got a little hole in it, and they're both connected up to a battery. Now this is a metal plate, and this is also a metal plate at the bottom. So what would happen? Well, if you notice, we haven't quite got a full circuit because there's a little gap between here. So we wouldn't expect to get a current under normal operation. And this is where the alpha comes in. Because we know that alpha is, one of the key things about alpha is it's highly ionizing. So what we can do, we fire alpha particles into this gap here, which is what we've got a alpha source for. Yeah, I'm going to fire some alpha particles into this gap. And this alpha source is constantly emitting alpha particles. And what do alpha particles do? Well, alpha particles are very highly ionizing. And that means that they can kick electrons off air particles. They kick electrons off air particles, we're going to get some positive ions. Let's add a few positive ions on there. And we're also going to get a few, if you're going to kick electrons off, then some are going to be winners and some are going to be losers. So you actually, whenever you create positive ions, you're going to also create negative ions. Now, what do we have here? We have negative ions, and negative ions are going to want to go up towards that positive plate. And the positive ions are going to want to come down to this negative plate. And these positive and negative ions actually, in effect, replace the role of electrons in the wires, and they actually enable this to make a full circuit. So we actually do, over here, in this is our ammeter, we start to measure a current. And that is fundamentally the key feature of a smoke alarm. And that's how they are generally going to be working during their life. They are going to be having ionization going on in this little chamber in here, which causes the ions to be formed, which allows a current to flow, and then we measure the current and we know the smoke alarm is working correctly. So what happens then to stop this process? Well, what can sometimes happen is if you're burning your toast, we might start getting some smoke particles in the room, and the smoke particles will fill the room and they'll fill the chamber eventually they'll get to the chamber of the smoke alarm, and you might get some in here and we might get some inside here. And the effect of smoke particles is that when they get inside this chamber, one, they can actually stop these alpha particles getting into this chamber in the first place. If they inhibit the smoke, because alpha particles aren't very good at penetrating, so if they hit into the smoke particles here, they will just be absorbed and they will not get through anymore, and they'll just get absorbed by those smoke particles. The other effect is once the smoke particles are in here, smoke particles can also absorb and just cling on to the ions, which means fundamentally we don't get any alpha particles, we don't get any ions anymore. So there's really no more ions going on in this central section here. And when there's no ions available to move here, because either the alpha particles haven't got there or the charged particles themselves have actually been absorbed by the smoke particles, then the current, instead of flowing, the current now stops. And if the current stops, then the smoke alarm is really going to send a signal out saying that there must be a fire. That'll be the signal. When you detect no current in this circuit, that'll be an indicator that there is some smoke in the air, and therefore the alarm needs to sound. We have to use, so important thing, the most common isotope used here is americium 231. It's very powerful ionizing because it's alpha. So, if you do have a smoke alarm, you certainly shouldn't be taking them apart, but, you can look here. You can see that, most domestic fire alarms, smoke alarms, will have this on here. So this one, it says here, it contains AM241, and that's the symbol for a very. See, you can spot that on the outside of most smoke alarms. Okay, another use. Let me explain what we're looking at here. Hopefully you can see here, this is a beta source. So what are we looking at? Well, what I'm trying to demonstrate here is the process by which either aluminium foil or paper is made in a paper mill. Now, fundamentally, what you do, let's just talk about paper. It could be paper, it could be aluminium, doesn't really matter. Generally with paper, you'd make some paper pulp and you'd make some sort of rough form of paper, it might be quite thick. And then when you're coming towards the end of the processing, you would then push the paper through two big rollers. And that would actually, if you wanted to push it hard, make it nice and thin. So if you push the rollers down really hard, you make it really, and if you release the pressure on the rollers, then you'd end up with thicker paper. So here's the paper coming in. This is the rough paper coming in, or the rough aluminium. And this is the final one coming out. And clearly, the more you apply pressure, the thinner the final product is going to be. Now, whenever you're making something like this, it's really key that you make the right size. You certainly don't want to be using lots of product up, making paper thicker than it needs to be, and you don't want to make the paper too thinner than it needs to be because it might break and have any other. So these are just quality control problems. So it's really key that the thickness of the final product is calibrated and done to the correct specification. So this is really where the beta source can come in quite helpful. If you look at here, we've got a beta source emitter and it's firing beta particles downwards and they're being detected. Now in this particular situation, I am getting, let's see, let's make it really thin. Let's make it really thin. And if I make it really thin, then you should really expect to see the same level of, the same level of beta particles on the other side because they're not really getting absorbed very much. But if I reduce the pressure a little bit and I make the paper thicker, well, what effect would that have? Well, that would in effect mean that more of the particles are being absorbed and not passing through. So you wouldn't expect to get so many going through when the paper is when the paper is thicker. You'd expect to get a smaller flow of beta particles making it down to the detector. Now, so therefore, if you're measuring the level on the detector, then you are in effect measuring the thickness of the paper of the aluminium. So in effect, you're actually just measuring the amount of beta radiation coming through, and your beta radiation is a surrogate, or just replacing the thickness of the aluminium foil or the paper. And obviously this is very good because it gives real-time measuring of the thickness, so you can make very rapid adjustments to the quality control of the paper. Okay, so they're more fundamentally the three that you need to know that quite commonly come up. I would suggest gamma radiation for these ones is quite straightforward. Well, gamma radiation is very good for sterilizing of medical supplies. These medical supplies here have been wrapped and sealed up, and really what you want to do is make sure there's no bacteria or anything on these syringes before they get used. So what you can do is you can seal them airtight inside plastic containers and then totally blast them with gamma radiation to kill any other bacteria that might be left remaining. A very similar technique is also used for foods. So if you're transporting seeds to another country, often what they don't, some countries don't want seeds coming in that are able to germinate. So you can actually do the same thing, and you can actually blast food with gamma radiation, and that might neutralize it and make it infertile. It can also kill bugs inside the food and any microbes inside the food that can affect the food quality, and all that can be done without any impact on without use of any chemicals. Another really good use is this thing here. Now I'll leave someone else to explain this. There's a great video here, so I'll put a link into this at the top. And this is the gamma knife. Gamma knife is a particular type of use of radiotherapy where they fire gamma rays from lots of different angles into a tumour. I'll mention one more thing here. Extension. We don't particularly directly mention about radio dating from using isotopes, but if you want to extend yourself, you could look at how we use radioactive isotopes to date organic materials. Okay, so summary: leak detection is a good use of beta radiation. That's a very good one. Also, the aluminium foil and the paper mill again is beta. Smoke alarm is alpha. You really need to know how to explain the fundamental basics of how a alpha detector smoke alarm works. And radiotherapy, cancer treatment, and tracers are uses of gamma. And you can find details of those in the video. So what I'd like you to do, make sure you complete your own little notes, use this video or use any other resources, use the book, and make your own notes on those three uses of alpha, beta, and gamma. Okay, now a little plenary. Match the radiation use, locating cracks in pipes, beta. Sterilizing medical equipment, gamma. Radiotherapy, that's gamma. Thickness control in a paper mill, or it could be an aluminium mill, that would be beta. Medical tracers is gamma. And a smoke alarm, well, that's the classic use of alpha. Okay, well, thank you for watching this video. Make sure you complete your work and complete any tasks that I've set for you on Firefly.